Okay, it's on, right? Okay. Good afternoon, everyone. Sorry, I forgot to bring my camera today. Uh, so we'll continue with axisymmetric problems. So the equation that we had arrived at last time was this. Okay. Now we have to solve this equation. How do we do it? What method do we use? So you must have come across some things like this in fluid mechanics. Perhaps in your first year of engineering maths also. So you are familiar with that e to the power mx strategy. So in a similar fashion, what we'll observe here is that this is second order, this is first order, but this is divided by r, and this is 0th order, and it is divided by r square. So there is something common here which we can exploit. The strategy here is to assume a solution form which is like this. Okay, we understand that u is a pure function of r. So the solution form that we are going to assume is this, r to the power m. The advantage here is that, you see, from here what I will get, m into m minus 1, r to the power m minus 2. Right? From this, I will get m into r to the power minus m minus 1, but these are divided by r. So I will end up with m into r to the power m minus 2. And over here, I will also end up with r to the power m minus 2. So this is the advantage. Okay. So from here, we will obtain m square minus m plus m minus 1 equal to 0, because r to the power m minus 2 is common. And from here, what we will have is m square minus 1 equal to 0, and that gives us m is equal to plus or minus 1. Which means that the general solution for u, it will be r to the power 1 as well as r to the power minus 1. Both of them are solutions, and the general solution or the complementary function, that will be what? That will be constituted of both these contributions. So it will be something like this. This is the general solution. Okay, so this is the r to the power 1 and this is the r to the power minus 1. Okay. Now what do we do from here? Well, you see, the unknown things here are these two unknown constants of integration. This a1 and a2, they are the unknown constants which we have to determine. So we have to use two conditions. So comparing with what we learned earlier, if we have a second order equation, we will need two conditions to find out the two unknown constants. Same situation here also. So what are the two conditions that we are going to use? Let us not forget what problem we are doing. We are still in mechanics of solids, and we are doing this thick walled pressure vessel problem. That is the original physical problem, the thick walled pressure vessel. So the thick walled pressure vessel, what are the conditions? So inside there is a fluid pressure Pi, and the outside there is a fluid pressure Po. Those are the only two conditions that we have at our disposal. Okay. So what are we going to use? So we cannot use any condition which is directly in terms of this u. Rather, it is in a somewhat different form. The actual boundary conditions are these. BC means boundary condition. Okay, so the boundary conditions are at r is equal to ri. Ri means what? Internal radius. If you have forgotten, so please write a small note here that Ri is internal radius. So at r is equal to Ri, we have sigma Rr is equal to what? Sigma RR is equal to, so please don't forget that we have our picture like this. This is our Pi, and from outside we have this is our PO. Okay, this is the radial direction. This is the radial direction. So on the internal surface, so on this internal surface, the sigma RR is pointing into the wall or out from the wall? Sigma RR is pointing out of the wall or into the wall? It is out of the wall. It is always out of the wall. Okay, this is sigma RR, and on this outer wall, on the outer periphery, sigma RR is pointing into the wall or out of the wall? Again out. Okay, this is sigma RR. So here also you note that sigma RR is equal to minus Pi, and on the outside wall also sigma RR is equal to minus PO. So sigma RR here is minus Pi, and at R is equal to RO, sigma RR is equal to minus PO. If you're not sure what is happening here, always think in terms of that little stress element. Earlier we had seen these kinds of things, this stress element. So if you have your x-axis like this, your y-axis like this, do we not write this as sigma xx pointing out, and on this wall also sigma xx pointing out? So it is exactly in this fashion. Okay, nothing fancy. So these are the two conditions. But the situation is that we do not know right now what is the expression of sigma RR in terms of U. Okay. So if we look back in our notes, what will you find? What is the expression of sigma RR in terms of the strings? I'll write something here, you please cross check. Is this correct? Okay. We had done this last time. Now, what we are going to do is, we are going to make the substitutions. What is epsilon RR and what is epsilon theta theta? So, epsilon RR is du dr, and epsilon theta theta, that is equal to u by r. This also we had seen last time. Okay. We had talked about those things, that in general it will be dependent on both u and v, but v is 0, theta dependence is gone. Because of those simplifications, we end up with these two expressions: epsilon RR is equal to du by dr or du dr, and epsilon theta theta is equal to u by r. Okay, so when we have that, so sigma RR becomes what? Let me do one thing, because I'm feeling a little bit lazy. This E divided by 1 plus nu, this particular combination, I won't write again and again. I'll just call it E dash. Please don't think that this is d dr. Okay. So E dash 1 minus nu epsilon RR. So this is du dr plus nu epsilon theta theta is u by r. Now we have to make we can make the substitution, that u is equal to a1 by a1 r, this thing, a1 r plus a2 by r. So what are we going to get? right? All right. So now let us simplify this a little bit. So you see, this is 1 minus nu a1 plus nu a1. So this is just a1. And then we have this a2 by r square. So a2 by r square, this one will be with a 1 minus nu, and this is plus nu. So this one will be what? Minus nu. Right? That's it. So overall we get E dash, we can bring back the original thing. So this one will be 1 minus 2 nu a2 by r square. So see, this E dash term multiplied with A1, that is one constant. And this E dash multiplied with this 1 minus 2 nu into A2, that is another constant. So overall, what this is looking like is this, that so sigma RR is equal to C1 minus C2 by R square. Okay. C1 minus C2 by R square. And if you proceed, like suppose we ask you like what is the expression for sigma theta theta. If you do like this, you will find that it comes out to be exactly the same thing except that it is C1 plus C2 by R square. Exactly the same C1 and C2. Okay, we don't need it here, but I'm just telling you. If you do the sigma theta theta, you can check. Okay, check sigma theta theta. Check the expression for sigma theta theta. It will come out as C1 plus C2 by R square. Now let us not forget what we are doing. We were trying to apply these boundary conditions. So let's do that. So at r is equal to Ri, sigma Rr is equal to minus Pi, which means that this is C1 minus C2 by Ri square. This is equal to minus Pi. And then we have at r is equal to Ro, that is the outer radius, we have sigma Rr is equal to minus Po, which means that C1 minus C2 by Ro square, this is equal to minus of Po. We have two linear simultaneous equations in C1 and C2. We have to solve for C1 and C2 and we'll get the entire thing. Okay, because if we obtain C1 and C2, we'll obtain the A1 and A2 also. Okay, we know the relations between A1 and A2 with C1 and C2. Okay, so the job basically boils down to finding out the these things, the C1 and C2 thing. Okay, so let's do that very quickly. So let's call this so what we'll do is So this one will be C1 Ri square minus Ro square, and this C2 will go away because I'm multiplying with Ri square here, Ro square here. It will be C2 here, C2 here. That will cancel when I do the subtraction, and I will end up with this thing, minus Pi Ri square plus Po Ro square. So overall this will be C1 is equal to Pi Ri square minus Po Ro square divided by Ro square minus Ri square. Okay. And for the C2 we can just subtract. So this one will be C2 1 by Ro square minus Ri square okay. So that's it. So we have our C1 and C2. All that you have to do is just take these things and put it back in the C1, the sigma RR expression, and you have the entire thing. Now, this is just the first thing that we expect you to do. Now, where do we go from here? So, what will happen is that in different kinds of situations, we'll not just be interested in the thick walled pressure vessel. The thick walled pressure vessel was just like an excuse for us to learn this thing. Whatever we have learned here can actually be applied to various other conditions. Okay, and we'll talk about that. But first, I want to discuss something related to this, but a slightly different kind of situation. So the entire thing was within the scope of plane strain. Remember, if you look back at your notes, I made a big deal about it, that this was the case of plane strain. Okay, where epsilon zz is equal to 0, epsilon z theta equal to 0, and epsilon zr equal to 0. But now I want to discuss a situation where we'll have plane stress. Now, you guys tell me, just a second. So, you guys tell me that if I want to investigate a case of plane stress, then what kind of physical situation should I be taking? This was the case of a thick walled pressure vessel, which exemplified the plane strain case. If I want to exemplify the plane stress case, then what kind of a physical situation should I take up? Remember what I told you earlier. If you have a long kind of thing, okay, a long member, like a beam, like a tube, these kinds of things are, whenever you have that, they are good candidates. I'm not saying that they will be plane strain case, but they're good candidates for plane strain. As opposed to that, when you have plane stress, then what kind of candidates would be good candidates? Disk. Okay, disk. So basically a thin kind of thing. So basically if you have this kind of a thing, okay, this flat version of this will be a good example of a plane stress. Now, just because it is thin like this doesn't mean that it will be plane stress. It will have to satisfy other conditions also, that there should not be any loading like this. The loading should be only in the plane of this. but geometrically this is the kind of thing. So if we want to exemplify plane stress, then we want to be dealing with a thin disk kind of a situation. Okay. So the drawing will look exactly like that. Whatever we have drawn for the thick walled pressure vessel, just two concentric circles looking from above. Okay, but the situation will be completely different. Yes, Charit.
We are discussing thick walled pressure vessels.
Yes.
So where is thick wall?
So the thick walled means that there is significant difference between the Ri and the Ro. So Ro minus Ri is still the thickness. It is T.
If I shrink Ri to R,
Then it will become the case of the thin walled pressure vessel. Okay. So you see, for the thick walled pressure vessel, so much we had to do, but for the thin walled pressure vessel, just like a very small derivation, right? Okay. So for the disk, what we are going to do is, let us start from here itself. I will not do all the steps of the thin disk. I will just outline it. You will have to do it yourself. So the thin disk is like this. There is a hole in the middle. Okay. This is the thickness. Okay. And the loading on this disk is in the plane of this disk acting radially. So the loading is like this. And behind also. Okay, so all around this thing. So if you look at it from the top, it will look just like this. And please accept that these are circles. Okay, very bad circles, but these are circles. So the loading is like this. So as I told you, it looks exactly like the thick walled pressure vessel. There can be loading here also. Okay. And it is not necessary that they have to be tensile in nature. They can be compressive also. Because this is no longer a fluid pressure. This is actual load, mechanical load. I mean, fluid pressure is also mechanical load, but you understand. So somebody is pulling on it or pushing on it. Okay, so this is the situation. So let's say that this load is given by the value Ko and Ki. Okay, Ko and Ki. So again, at R is equal to Ri, we are going to have sigma Rr is equal to Ki. Oh, sorry, Ki, yeah, right. So see here, unlike the pressure case, which was pointing inward, here the Ki is along the direction of the sigma Rr. Here also the Ko is along the direction of the sigma Rr. So we don't have to use the negative sign. But what is the governing equation? That I am not telling you. Okay, so how do we go about doing this? Well, the situation is such that you tell me, what was my original governing equation? Where did I start the entire story from? You look back at your notes and tell me. In the case of the thick walled pressure vessel, which exemplified the plane strain case, which was the equation that I started out with? I started out with the stress equilibrium equation. Very good. Okay, in the radial direction. I started out with the stress equilibrium equation in the radial direction. Now, given axisymmetry, given the condition that there is no load in the theta direction, what is the equation that we started out with? Please take a look back at your notes. It's there. what did the stress equilibrium equation in the radial direction reduce to under the conditions of axisymmetry and no load in the theta direction? Right. So the governing equation still remains this: d sigma rr dr plus sigma rr minus sigma theta theta divided by r is equal to 0. Okay, what is this? This is the stress equilibrium equation in the radial direction under the condition of axisymmetry plus okay. So where did we go from here? We went to the equation which was completely in terms of the u. And how did we do that? We took this sigma rr and sigma theta theta, we expressed them in terms of the strains. And then we expressed those strains in terms of the displacements. And that is the exact same story that we have to follow here also. Okay, except that now we are in the plane stress case. Plane stress. Plane stress means what? Sigma zz is equal to tau z theta is equal to tau zr equal to 0. Okay. Now, what do we need? We need the sigma rr and sigma theta theta only. Let us start from the generalized Hooke's law. Epsilon rr is equal to 1 by E. You actually know this. You have already been tested for this. I have lost track of which class test we are going. Okay, million number class test. Okay, so the one that we had last week. There were 2 questions on plane stress, right? There were. Plane stress, plane stress. It was not plane strain. If you had done plane strain, then anyway, I'll do it. By the way, you guys tell me, are you enjoying this series of class tests almost every week? Huh?
Sir, I don't know whose decision was it to keep it 40%.
I am not enjoying it at all. Every alternate week I have to set questions. I'm not enjoying this at all. But somebody in the beginning of the semester, some of you had told me ki just don't keep 2 class tests because 40 marks riding on just 2 class tests is a little bit dangerous, which is also logical. I mean, it's a little bit irritating to have. You just stop. You stop. You are getting very good marks. You have no right to say anything.
2 classes before midterm and 2
Yes, I know. That would have been fair. But there are more important things, right? Like Kshitij and Springfest. So those cannot be sacrificed in front of just small things like academics. Okay. रोहित ये सब काट देना. Okay, listen, come back. So sigma zz is 0. Okay, sigma zz is 0. So what do? We find out the expressions of sigma rr and sigma theta theta from these 2 things. Please find it out. Do it quickly. It will come out like that. E by 1 minus nu square something. Okay, do it quickly. Yes, tell me. So Rohit, I forgot my phone today. This is Chad's phone. That is why he is so concerned. He does not love me, nor my phone. Everyone has a special relationship with their phone. Okay. So again, the same equation you are going to get. But the problem is that this is the problem, that in the examination we are not going to tell you whether this is a plane stress case or a plane strain case. We're just going to tell you that this is the situation, thick walled pressure vessel or disc, and you have to figure out whether this is plane strain or plane stress. Now that equation is the same. You will get at least half the solution correct if you start from that equation. And then when you come to the expressions of the stresses, nothing will go right if you pick the wrong case. So if you pick plane strain for the plane stress case, everything will come out wrong. You will think that Young's modulus is there and Poisson's ratio is there. So it looks almost the same. So why is that not giving me marks? But it's completely different. Okay. So your seniors have done all sorts of permutations and combinations in doing these kinds of mistakes. So I'm warning you beforehand. Please be very careful. Even if you do some mistake and maybe instead of new, it comes out as twice new. Maybe you made a silly mistake somewhere and then everything is wrong. But you have identified this thing as correctly as plane stress or plane strain, you will get more marks than a student who has done the entire thing correctly, but he has chosen plane strain in case of plane stress. Okay. So the conceptual understanding is more important. All right. So once you get this, again you are going to get the solution as A1 by R. Sorry. A1R plus A2 by R. And then from here, you are going to utilize the boundary conditions that sigma RR is equal to Ki at R is equal to Ri, and sigma RR is equal to Ko at R is equal to Ro. When you do these kinds of things, you will again get some expressions. Okay. So, I mean, every time we give you a problem, you have to go through these things. Okay. And this is where I mentioned earlier, the girls outshine the boys disproportionately. I don't know what is there in these problems. There is maybe some kind of an organization or systematicness to it. They're just better at it. Now, what I want to discuss is some variations over these boundary conditions. Okay, maybe it looks a little bit more like fluid mechanics. I don't know. I want to discuss some boundary conditions. Everyone, please wake up. Okay, and listen to this. Here, this is, I have written this in terms of this Ki, in terms of the sigma RR. But suppose the situation is like this, that there is a pillar. Okay, there is a pillar, and we have, like, when in a very tight fitting, we have through like this hole, we have taken this disc and we have fitted it onto that pillar. Okay, so we can think of it like this, that this is the pillar and you have a little thin disc which I have fitted over here. So this is a very tight fit. So in the inner periphery, if I pull on it, and you imagine that's like with proper Fevicol or some bonding, it is properly fixed. So then what is the condition there? So if we say that the inner periphery is fixed, okay, this is a separate problem we are doing now. That previous problem is over. I'm not going to do it anymore. Suppose I say that this inner periphery is fixed. Outer periphery is like this only. Then what is the condition I should write at r is equal to Ri over here? You tell me this. Fixed means what? Fixed means what? The material points which are present on this periphery, they are not allowed to move in the radial direction. Then what is the meaning of that in mathematical terms? Displacement is 0. Okay, displacement in the radial direction is 0. Okay, so u is equal to 0 for fixed condition. Please remember this. Okay. At r is equal to Ri, it is still sigma Rr is equal to Ko. Okay. So this is the thing. Opposite to this, we can have a situation where this fixed thing is no longer in the outer periphery. It is in the inner periphery. So suppose we say that this fixed thing is at the outer periphery. This is fixed. And maybe over here, there is this kind of a load, which is Ki. Then for this case, what will be the thing? At r is equal to Ri, what will it be? Sigma Rr is equal to Ki, and at r is equal to Ro, what is it? Here it is fixed. Okay, fixed means u equal to 0. Don't be afraid to say it. U is equal to 0. When you do these kinds of cases, the solutions will come out significantly different. And this also your seniors have done. I have taught in class maybe the thin disk or the plane strain case of the thick wall pressure vessel. In terms of sigma RR and sigma theta theta, we have talked everything. But when I ask this variation of the question, they still vomit out that thing only, which I have taught in class. Okay. Now, this is for the disk. You can have the exact same thing for the plane strain case also. Okay, for the thick wall pressure vessel. Exact same thing. Nothing changes, but of course, your final expressions of the answers will change depending on whether it is plane strain or plane stress. Okay. Now, once we have these kinds of situations, then we can explore other kinds of situations also. Meaning, see, all through your, from the beginning of your semester, maybe even starting from your basic engineering mechanics, we have talked about situations like this, that given this kind of a loading, investigate such and such a situation such that the stress at such and such a point does not exceed the yield stress value or the allowable stress value. So we can have a variation of these problems where we say that maybe the internal pressure is this, and find out the external pressure such that the sigma RR at such a radius does not exceed the allowable stress. Okay, ultimately you have to go through all of these steps only, but you be careful like what we are asking for. There is another variation to this. So if you look at the tutorial sheet number 9, which is now drawing this on this flat board, it is a little bit dangerous because every time it looks like two concentric circles. Okay, it looks like two concentric circles. This is a spherical vessel. Okay, so maybe I draw something like this to denote that this is some kind of a 3D picture. So this is a spherical vessel. Here also the internal radius is Ri, the external radius is Ro. However, the difference is that, and this will not ask you to derive, okay, because the derivation is a little bit more involved. For these kinds of problems, if I give you spherical vessel, then as you'll see in the tutorial sheet, I have given you that the governing equation starts from here. Just the small change is here. Just this 2 is here. Nothing else changes. Okay. Of course, when you do the problem for the spherical vessel, it is neither a case of plane stress nor a case of plane strain. So what is it? So the special thing about the spherical vessel, the special thing about the spherical vessel is that if it is having this kind of a perfect spherical symmetry, then you know that the spherical coordinate system is what? R theta phi. You have probably learned it in physics, R theta phi. Now, is there any difference between the theta and the phi if you have perfect spherical symmetry? What is R theta phi? So let's say that you have your x like this, your y like this, and this is your z. So any general point, okay, this is your R, okay, maybe this is your theta and this is your phi, right? Do you remember these things? Huh?
I is from Z.
Sorry?
I is from Z.
Doesn't matter, phi or phi dash, it doesn't matter, okay. Oh, sorry. This is your R. Okay. Now, if you have perfect spherical symmetry, is there any difference between the theta and the phi? There is not. Okay, so theta and the phi are exactly the same things, which means that when you have your this thing, the generalized Hooke's law, you have this situation, but theta and phi, they are the same thing. Same thing means they are interchangeable. Okay, so for spherical symmetry, theta is equivalent to phi, which means that epsilon RR is going to be equal to 1 by E sigma RR minus twice nu sigma theta theta. Similarly, your epsilon theta theta, that will be sigma theta theta minus nu sigma RR plus sigma phi phi. And this will be equal to I've just substituted sigma theta theta equal to sigma phi phi. That's all. And you do not have to worry about epsilon phi phi because it will be exactly the epsilon theta theta. Okay. So knowing this, you can again start doing the substitutions, proceed as before. Okay, use the boundary conditions as before. So you can have lots of different variations on this. What is the time now? 4. Just hang on. I want to say something else. Suppose I come back to this thin disk problem only. Okay, but instead of one material, I have two materials. Okay. So suppose I have this situation. So the first material is material A, and then we have material B. And the condition is that these two things are perfectly bonded at this interface. Okay. Then what? Okay, you want to talk about the boundary conditions. All right. So outside, again the same thing as before. But you see, these two conditions are not going to be sufficient. Why not? Because for this material A, which is inside, you are going to have one particular governing equation. And for the outside material, you are going to have another governing equation. Why is that? Because the material properties are actually different. Because the Young's modulus and the Poisson's ratio can be different. Which means that you will have to now deal with two governing equations. Okay, just leave it. So the material properties are going to be different. Now, for this material which is inside, you have this condition, sigma rr is equal to ki. And for the material which is outside, you have the outer condition that sigma rr is equal to ko. But what happens at the interface? So at the outer periphery of the inner material and the inner periphery of the outside material, what is the condition?
That those two equations value will be same.
Values will be same. What values will be same? Displacement values will be same. But if we say, let us say that R is equal to, let's say something like Rm. Okay, R middle. Okay, let's say this is the R middle. At R is equal to Rm, we say that U is equal to U. U means U1 is equal to U2 or UA is equal to UB. Then how many total conditions do we have? 3 conditions. But we have 2 second order governing equations. See, from the inside, you are going to get this thing. D square U1 dr square plus 1 by r du1 dr minus u1 by r square equal to 0. And for the outside, you are going to get d square u2 dr squared plus 1 by r du2 dr minus u2 by r square equal to 0. So you have 2 second order differential equations. From this you are going to get A1 and A2. From this you are going to get A3 and A4. But you have only 3 conditions over here. Okay, you will not be able to find out all the unknown constants. So you need another condition. The other condition is that okay, the radial stress should be equal to. Now, please don't think that I'm just pulling it out of thin air, these things. They actually have a formal basis behind them. So we arrive at them formally through the equality of fractions, but don't worry about them right now. Okay.
So, are they equal?
So think of it like a tension occurring at this. So by how much this thing is pulling on this is also pulling on this by the same amount. Okay, so that sigma rr, the radial stress acts like a tension. That's it. Take a break.
Would there have been any difference if this was a spherical vessel instead of?
Then also exactly the same kinds of conditions. Okay, please take a break.